All right, so remember that derivatives, they measure the instantaneous rate of change, right? So this idea was considered by mathematicians, and they develop applications for that. One application is this. One application for derivative is to estimate the final output value given a small change on an input value. How does this work, Professor? Well, imagine you have a function, right, whose graph is this over some interval here. And suppose you allow yourself a change that is small. Let's call it age. So if your input value A is increased by a small amount age, the new input value has to be A plus age, right? A plus age. Now, A via the function should be paired up with f of A plus h should be paired up with f of A plus h, right? We have that. But now let's try to see what should be the derivative of this function evaluated at A. Okay, what would be that? Well, we know based on previous lectures that that derivative is gotten by taking the limit as h approaches 0 of the slope of this secant line, right? The secant line. And we have showed this before. There is even an animation that probably I will show again. Yeah, but this is basically saying this, right? If you take the slope of this secant line and you approach from Q to P gradually, right? Eventually, you will get here to this base point P, and this is what mathematicians call the derivative, right? The slope of this tangent line. Let's see. Let's check this. Okay. Draw a tangent line there. Yeah, so this, right? This is the tangent line, right? So these guys, again, if you have difficulties figuring this out or interpreting this, I strongly recommend you to look at our website. It's an animation. It tells you how from a secant line, this is the point Q, this is the point P, the base point, right? If you approach to your base point little by little, the secant line eventually becomes the tangent line, right? And when that happens, when h, the horizontal distance, when h is 0. When h is 0, the secant line becomes the tangent line, right? They're the same. Great, right? And at that point, you can say that you can find the derivative, right? Yeah, great. Play around with this animation, guys. It will help you to understand a lot of ideas here, concepts. So now, but what is this? Limit of f of h plus h minus f of a over h. If f is small, I can say that this slope should be basically equal to the slope of the tangent line, right? If h is small, if they are very close, because you saw it in the animation, right? When you are far away, when you are far, they are not the same. But when you are very close, notice how close the two slopes are, because basically the secant line becomes the tangent line, right? Right there, you cannot see a difference between the slope of the secant line and the slope of the tangent line, right? So this is why h is close to 0. So mathematicians then said, if h is small, then the derivative is approximately equal to this slope, right? You can drop this limit and say, okay, these two guys are approximately equal to each other, right? And from there, if you work this out, right, this approximation by multiplying both sides of this equation by h, notice h cancels here, and I will have that h multiplied by the derivative is equal to this difference, f of a plus h minus f of a. working this out further, meaning adding this f of a to both sides, what do we get? That's f of a. Well, this is 0. This guy, which I have written here, this guy here, is equal to what? This times the derivative plus f of a, right? Or equivalently f of a, the evaluation at the base point A, plus the contribution of the derivative, this h times f prime of a, or equivalently f prime of a times h, right? Yeah, very good. This formula, which is an approximation and it works when h is small, is called the amount of change formula. Amount of change formula, and it's very useful, guys, this formula. You may say, why, professor, is useful? Well, for example, right, suppose you are dealing with, you are the CEO of a company, you're dealing with the production, and somehow you have a function that controls your cost. And you want to know how much the cost will be affected if you change the production by 1 unit, a small change, right? So if I increase by 1 unit my production, how my cost will be affected. You can basically compute in your head how the cost will be affected by multiplying the derivative times that little change 1 and adding to that the evaluation of the function at the base point, right? So it's a very useful formula, has a lot of applications. Now, let me show you just a quick example because we're gonna move to applications in physics, right? Which we're gonna work on in detail, but at least let me show you this. Later on, we will go over this more in details in another section. Example, right? Suppose you have the knowledge of your function evaluated at some base point 3, that is 2. And you have also knowledge of the derivative at your base point, right? 3 is 5. And let's say you want to figure out what should be the value of this function if you allow yourself a little increase to the base point. A little increase to a little point. And let's say evaluation of the function at the value 3.2. I say a little increase, guys, because maybe I can write here, right? 3 and here 3.2. Compare these two. To go from 3 to 3.2, you need to add 0.2, right? This guy is small with respect to 3. Respect to 3, or relative to 3, right? To 3, right? Because it's almost like 10% of 3, right? This is how this word small should be understood, right? Small, relatively speaking, right? Relatively speaking, as a percentage of your base point, right? So yeah. All right, so I noticed that this 0.2 is small. So then when I compute this f evaluated at 3.2, I write this 3.2 as this, as a sum of 3, plus 0.2, right? And this guy we know is small compared to 3, right? This guy is small compared to the number 3, all right? Now, then, since this is small, I can apply the amount of change formula, right? That I wrote here. I can say that this guy is going to be equal to the evaluation at the base point 3, which is something that is given, plus the contribution of the derivative, right? The contribution of the derivative f prime at 3 multiplied by this little change, 0.2, right? I am applying this formula, right? Because the change again is small. Okay, and this guy is given, right? They are here both. Right? F of 3 is 2, I know this. f prime of 3 is 5. I know that. So I can compute this, right? I can estimate nicely this f of 3.2. 3.2. Yep. So this guy was given is 2 plus this guy also given 5 times 0.2. Now you just put this in the calculator and that's it, right? That's it. This guy is just this. And again, guys, this is a way to estimate output values whenever the change on the input values is small. Yeah, and I get the number 3, right? So the number 3 should be a good estimation. So great, number 3. Very good, very good. All right, but this again, we will do this later when we look at linear approximations. I think it's called linearization. It's some chapter that will come in the future, but for now, get the idea. And let's go instead over this part. It's called motion along a straight line, where we will do some work on the worksheet. So let's talk about this, motion along a straight line. A physicist realized that if a particle is moving on a straight line, that can be completely modeled using calculus, in particular using derivatives. How? Well, suppose you are giving s of t, which is going to be called a position function, a function that gives you the position of the particle at a given time. Well, then the velocity should be computed as the variation on the position over the variation over time, right? Over time. This, remember, this Greek letter delta is used to indicate variation. Delta, right? Comes from the Greek alphabet. This means just change of position. Change of position. Right? Mathematicians are minimalists. Instead of writing change of position here, they write delta position. Change of position is what they mean. Similarly here, when you see this triangle, this the Greek letter delta, this means change of time. Change of time. So if you divide change of position by change of time, you get the velocity, right? The velocity. But this velocity, turns out, as I explained, can be gotten by just taking the derivative of this position function, right? With respect to time, right? With respect to time. So velocity will be the derivative of the position function, okay? That's the connection with calculus here, right? Velocity derivative of position function. Similarly, physicists often talk about acceleration as the change on velocity over a change on time, right? Delta of velocity over delta of time, change of velocity over change of time gives you the acceleration. The rate of change of the velocity, instantaneous rate of change of velocity to be precise, right? But turns out this acceleration can be computed as the derivative now of the velocity function. Derivative of the velocity function gives you the acceleration, okay? B prime t, derivative of the velocity function with respect to t, acceleration. All right, so now something else. Note, big note here, is speed. Sometimes they will ask you to figure out speed. It's just the numerical value of the velocity. The velocity has a direction. You could be moving in this direction to the right. You could be moving in this direction to the left. In this, right? So in this case, velocity positive. If you are increasing the position over time, if you are decreasing your position over time, negative, right? Velocity has a sign, but the speed doesn't have a sign. So speed is defined as the absolute value of the velocity, right? Yeah, maybe I should write here absolute value, this absolute value. Absolute value. of velocity. Gives you the speed, okay? So now example, let me give you this example for you to understand how this works. It's related to free fall. A ball is dropped from a height of 64 feet. Its height above ground in feet, t seconds later, is given by this position function. S of t equal negative 16 times t squared plus 64. Physicists figure this out, right? By experimentation, by comparing height over time, the position function is given, okay? Now, they include this diagram for you to kind of understand what's going on, right? The ball is dropped at this height, 64 feet, right, which is here. And then the heights, they decrease over time, right? Decrease over time as time passes by until a certain point there is no longer height, the ball reaches the ground, right? So questions, 4 questions here. First question, find the velocity of the ball 1 second after it was dropped. Right? Then second question, find the instantaneous velocity of the ball when it hits the ground. Third question, find the speed of the ball when it hits the ground. D, find the acceleration of the ball. 4 questions to answer, right? So let's start with the first one. Find the velocity of the ball 1 second after it was dropped. For that, I remember that the velocity can be found by taking the derivative of the position function, right? The position function is given there, is minus 16t squared, minus 16t squared plus 64, right? And quickly I get the velocity by taking the derivative of the position function, right? So I can answer the first question. The derivative of this position function is gonna be, look, this negative 16 is a constant, comes outside, 2 comes down up front, 2 times negative 16 is negative 32, right? Negative 32, t raised to 1 less than 2, 2 minus 1 is 1, I don't have to write it, plus the derivative of 64, but the derivative of this constant 64 is 0. So this is the derivative, minus 32t. Now they are asking me to figure out the velocity of the ball 1 second after it was dropped, right? So I just say, okay, let t be equal to 1 second, right? 1 second. And all I gotta do is then substitute in my velocity function t with the number 1, right? With the number 1. So this t is gonna be 1. So this is this. So the velocity after 1 second when the ball is falling should be just this, negative 32, right? Negative 32. In the end, attach the units. They are measuring distance with feet, time with second, right? So feet per second. Negative 32 feet per second should be the velocity after 1 second, right? So let's say 1 second is here. After 1 second, this is falling, right? Notice less and less distance over time. Distance decreasing over time. That is why the velocity is negative, right? Negative. So this answers A, right? This is part A. Let's answer part B. Part B says, find the instantaneous velocity of the ball when it hits the ground, when it hits the ground, right? Meaning when the ball is here, right? When the ball is here, when it hits the ground, right? Ball hits the ground, right? Notice this is when this is measuring the heights, right? When the height is 0 is when the ball will hit the ground, right? Hit the ground. H height equals 0, right? Height 0. Okay, so let's do that, right? Let's find out where, or better say, at what time the ball will hit the ground, right? The ball will hit the ground when S equals 0, right? The distance, right? This I wrote H, but probably will be better if you write S because it's the position, right? Vertically measure S is 0. When S is 0, the ball will hit the ground. So at this point, you can understand the height when you look at it. So now, then you set your distance, your position to be 0 to find out when the ball will hit the ground. Notice this is S of t. It's a function, right? It's a function that physicists figure out, right? It's given. So set that equal to 0 and solve for t, right? To find out what time, after how many seconds, the ball will hit the ground. Well, here you can solve these guys any way you want to solve it. There's factorization, there is isolation of the variable, many different ways to solve this, but one way is this. When you divide both sides by -16, you will get that t squared equal 16 into 64 is just 4. And when you take the square roots in both sides, right, t equal plus minus the square root of 4, 2. However, guys, we are dealing with time, right? With time. And time only makes sense when it's positive, right? The mathematics is telling me that there are two possible solutions for this equation, right? +2, -2, but physics, the real world, is telling me that only this makes sense, right? This does not make sense, right? Does not make sense. Since time is positive. It grows in just one direction, right? Great. All right, so now the ball hits the ground at t equal 2, right? That should be our conclusion, right? The ball hits the ground at t equal 2 seconds, right? 2 seconds. Okay, so then in the velocity function that we have, right? Do we have the velocity function, Professor? Yes, here it is, right? -32t. In that velocity function, substitute t with the number 2. That's all we gotta do. Our velocity function was -32t, but t is equal to 2. So this should give us the answer, right? -32 times 2. That is -64, right? -64. And in the end, you may attach the units feet per second, right? Feet per second. Negative again, because the ball was losing height over time, right? Good. But let's see, let's check the answer. The question, sorry. Find the instantaneous velocity of the ball when it hits the ground. Done, we got it, right? This is it. This. Now, next question, part C. Find the speed of the ball when it hits the ground, the speed. C, find the speed. Anyone could tell me what is the speed here, knowing, you know, that the speed is just the absolute value of velocity? Remember, speed, you take just the value of the velocity. You don't consider the sign, right? The absolute value just picks up the value, not the sign. No. See the chat. Yeah, I'm glad you guys picked this up. Great, excellent, excellent, Sarah, excellent, Adriana. Yeah, good thinking. Very good, right? What would be just the absolute value of this guy? Well, if we take the absolute value of 64, that's just 64, right? So 64 feet per second is the speed. Same value as the velocity, but the sign is positive, right? That's all that changes. So that answer C, right? Very good, guys. Part D says find the acceleration of the ball. Acceleration of the ball. Part D, acceleration of the ball. The acceleration of the ball, remember we said, must be seen as the derivative of the velocity, right? Because it's the rate, the instantaneous rate of change of the velocity with respect to time. So you take the derivative of your velocity function. But the velocity function, we found out, is just this, negative 32t. So we got to take the derivative of that function. But what is this derivative? Anyone could tell us what's the derivative of negative 32t? I see. Movement on the chat room. Excellent. Sarah, Adriana, Oscar. Good, guys. Very good. It's just negative 32, right? Because it's a constant. We have these properties for derivatives. The constants come out. Derivative of t is derivative of the identity function is 1. So this times 1 is just minus 32, which should be measured in feet over or per square second, right? That's how you measure acceleration. And turns out, guys, since this is just free fall, right? You're letting an object fall. This is what is the acceleration of gravity. Right? Neglecting the effect of the air, right? Yeah, acceleration of gravity. Excellent. It's a constant. All right, so now let's go ahead and work some exercises. So let me show you this one, the first one, and then I will let you do number 2, okay? For the first one, it says the function s equal f of t gives the position of a body moving on a coordinate line with s in meters and t in seconds. This is the function. Question, find the body's speed and acceleration at the end of the interval. They're giving you an interval for your time. T goes from 0 to 2 seconds, right? So at the end of the interval means at this value of t, right? At the end of the interval. Okay, great. So how this works? Well, let me give you this example, right? Then you will do the next. S is equal to 2t squared plus 4t plus 6, right? That's as a function, our position function. They want the velocity, right? But velocity, remember, is just the derivative of the position function, right? Derivative of the position function. And what is the derivative of the position function? Well, derivative of this part, 2 comes down, multiplying 2 is 4t plus derivative of this guy, 4 is a constant, comes out, derivative of identity function t is 1, 4 times 1, 4, right? 4t plus 4, derivative of the constant function 6 is 0. Great. Now, they want this velocity at t equals 0. How do you know it's at t equals 2? Sorry. How do you know, Professor? Well, because it's at the end of the time interval. Time interval is from 0 to 2, so at the end of the time interval should be at t equal 2, right? So just substitute t for 2 here, or with 2, and this should be the velocity evaluated at 2, right? Or after 2 seconds. This is 8 plus 4, just 12. In the end, feel free to attach units. The position is measured in meters. The time is measured in seconds, so meters per second, right? This is the velocity. Now, they want the speed, right? But no problem, the speed is just the absolute value of the velocity. So absolute value of 12 is just 12 itself, right? It's positive meters per second. So done with the speed. Now they want the acceleration, but the acceleration, remember, is the derivative of the velocity, right? V prime. The velocity is this function, 4t plus 4, right? So basically, I have to take the derivative with respect to t of this guy, right? 4t plus 4. But what is that after we distribute our derivative? So acceleration will be the derivative of 4t is 4 comes out, and derivative of t is 1, 4. Derivative of 4 is 0. So this should be the acceleration, right? The unit should be meters per square second for acceleration, right? They're working in the international system. So that's it. So the one that you have to choose, be careful with the units, should be this one, right? Look, 12 meters per second is velocity. They want it actually the speed, be careful there. They might not be the same, right? So the speed is what they want it. The speed and then the acceleration, right? The speed and the acceleration. The acceleration is, that's it. So can you follow these guys and try to number 2? And then we will go over other forms that are trickier. This one. Yeah, but first these two. Let's master this part. Mm-hmm. 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 They give you the position function again, and they are asking you to figure out the speed and the acceleration at the end of the interval time, right? So time interval, at the end of the time interval. And as a hint, end of the time interval for us will be now 3, number 3, right? The number 3 at 3 seconds. No. Yeah, great. Mm-hmm. Yeah, let's start this out. Yeah, body acceleration. Yeah, great. Acceleration. Mm-hmm. Yeah, hint, be careful when you go from velocity to acceleration, right? Be careful there. Mm-hmm. Mm-hmm. Yeah, take the absolute value, right? Yeah, very good, very good. Mm-hmm. Mm-hmm. Uh-huh. All right, let's just start this out. Let's try to work this out together, okay? Find the body's speed and acceleration. For the speed, I need the velocity. So I'm gonna start by writing out the position function as 3t minus t squared, okay? I see students posting answers. Adriana, very good, very good. Mm-hmm. Yeah, you got it. Excellent, excellent, good job. Yeah, great. So this is a position function, right? Now I want the speed, but to get the speed, I have to find the velocity. So the velocity is the derivative of the position function, right? So we go ahead and say, okay, what's the derivative of this guy? Derivative of this guy is 3 coming out. Derivative of t, identity function is 1, 3 times 1, 3, right? Minus here, derivative of this part, 2 comes down, t stays with an exponent 1 less. 2 minus 1 is 1. We don't have to write it. This is the velocity, right? But now they want this velocity, not in general. They want this velocity at t equal 3. Professor, how do you know it's at t equal 3? Well, because they say they want the velocity, the speed, right, and the acceleration at the end of the time interval. This is the beginning of the time interval, this is the end of the time interval, t equal 3. So we just have to substitute this in here, right? So as a result, the velocity evaluated at 3 will be 3 times 3 minus, sorry, 2 times 3. But notice that this is a tricky result because this will be 3 minus 6, right? And 3 minus 6 is negative 3, right? Negative 3. Professor, negative velocity. Yeah, it just means that the object is losing, the position is getting smaller, it's decreasing over time, right? That's why the velocity is negative. Now, but now they want the speed. You gotta remember, guys, speed equal absolute value of velocity. So it will be the absolute value of negative 3. But the absolute value of negative 3 is 3, is positive 3, right? 3. And in the end, we can add the units meters per second, right? So done with the speed. Now, for the acceleration, remember the acceleration should be taken as the derivative of the velocity function. The velocity function is here. So we're going to take the derivative with respect to time of this guy, 3 minus 2t. Then acceleration will be equal to what? Derivative of this guy, 0, right? 0, no derivative. Derivative of this guy, minus 2 constant, multiply the derivative of this is 1. So minus 2, right? Minus 2. In the end, attach the units meters per square second. That's how you measure acceleration, right? Meters over square second. So this is telling us that the answer for this question number 2 should be just this guy, right? 3 meters per second speed, acceleration minus 2 meters per square second. Okay, great. All right, so this was one application. Let's look at this one. Probably you can do this at home, find the body speed and acceleration at the end of the time interval. Similar is just with a cubic function, so you should be okay with this. But I want to go over the tricky ones. This one I think is tricky. Let me explain this to you, and then I will ask you to do the next number 5, okay? Yeah, this is similar. Yeah, here it says the driver of a car traveling at 36 feet per second suddenly applies the brakes. The position of the car is S equal 36t minus 3t squared. T seconds after the driver applies the brakes. How far does the car go before coming to a stop? Before coming to a stop. Okay. Let's figure this out together, okay? For that, I'm gonna draw a diagram that hopefully will help us to understand this. So let's say the car is here, and then brakes are applied. After the driver applies the brakes, the car moves, still moves slowly, probably, right? But still moves, and eventually stops. Okay, so here, stop. Car stops. All right, so then they're saying, right, that the position from here to here, right, is controlled by this function, 36t minus 3t squared. They're trying to figure out what is this distance, right? It's how far does the car go before coming to a stop. But in order to do that, I have to find how long it took, right, for the car to go from here to here. So how many seconds pass between this point and this point, right? So that I can find the distance. So I gotta find out at what time this car stops, right? For that, guys, after you compute your velocity, which is gonna be the derivative of your position function, which is gonna be this 36 derivative of this part minus 2 times 36 t derivative of this part, right? This is the velocity, right? But I need to find out at what time it stopped, the car stopped, so that I can find this distance, right? But notice, guys, that the car will stop when the velocity equals 0, right? When v is equal to 0, right? I have v as a function here, right? So we set v equal to 0, this function, right? To find out for which value of t the velocity will be 0 and therefore the car will stop, right? So let's solve for t. Yeah, a little bit tricky here, but again, guys, when they ask you this question, just set your velocity equal to 0. That will tell you when the car will stop. Divided by -6 both sides here, t equal 6 into 36, 6, negative and negative positive. So t equals 6 seconds. So this is telling me that after 6 seconds, the car will stop, right? The car will stop. They want me to show what is this distance from here to here, right? So I have a position function. All I have to do now is this. I have this position function, right? The one that gives me the position as a function of time, right? Is this. So I just gotta let t be 6, right? 6, so that s of 6 will be the distance that the car travels until it stops, right? So 6 here, 3, 6 squared. This, guys, I suggest you compute this in your calculator because it's gonna be difficult to do it in your mind, right? So bring your calculator. I'm using our Desmos scientific calculator available for you to use in our website in Blackboard, right? You can use this also for your exam. All right, so I got 108, right? 108. 108. In the end, attach the units. They were measuring distance here in feet, right? In feet. So it will travel the car after the driver apply the brakes. It will travel 108 feet, right? That will be the distance. It will go 108 feet and then it will stop, right? So this 108 feet, right? Very good, guys. So answer here. A very tricky question. If they ask you for the time, set the velocity equal to 0. If they ask you for the distance, then once you get that number, you plug that into your position function number to get this. Now, this one is a little simpler because they don't ask you for the distance, they just ask you for the time. So can you try this one? No? Number 5, try. Okay. It's a little bit simpler, so maybe I can draw a diagram too. So as a hint, right? It's a car. The driver applies the brakes. The car stops eventually, and that stop is just when the velocity is 0, right? So car brakes are applied. Yeah, do this one, guys. And then car stops. They are asking you how long it takes, right, for the car to stop after applying the brakes. Try to figure it out. Follow the previous example if needed. Mm-hmm. Mm-hmm. Yeah, try to remember this on your homework. I think there are a couple of questions related to this part in the homework that might have already in your account now. Mhm. I see. CG. Yeah. Very good. Very good. Yeah. Great. Great. Yeah. You got it. Yeah. Excellent. Excellent. Yeah. Excellent. 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 Good. 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 So let's do it together, guys. So I want to show you one more form. So again, let's try to do what we did before, right? We start by writing out our position function here is 30t minus 3t squared. And then quickly we get the velocity, right? Because we're gonna need the velocity to find out when this will stop. Yes, Sarah, very good, very good. Adriana, also very good, guys. Good, good that you're picking this up. Yeah, and try to remember this for your homework. It will help. And also in the exam, I think one question probably is related to this part. So the velocity is the derivative of the position function, right? So we take the derivative S prime, right? That's the derivative of S. And that derivative will be the derivative of this part, which is just 30, right? 30. Minus the derivative of this second term. 3 comes down, comes out, right? 2 comes down, 2 times 3, 6. T raised to 1 less, which is just 1. This is the velocity, right? Velocity. Now, one thing is true. When this car is going to stop, car will stop when the velocity is equal to 0, right? When the velocity is equal to 0, right? So you set v equal to 0 and solve for t, right? That's all we gotta do here. All right, our velocity function is this, 30 minus 6t, right? That should be equal to 0. And all we gotta do is just to solve for t. Many ways to solve this equation for t. I'm just following this one. Minus 60 equal minus 30. Dividing both sides of this equation by -6. This time it gives me just one solution, which is this. 6 into 30 is 5, right? 5. In the end, you may attach the units. Notice we are measuring distance in feet and time in seconds. So feet per second. Yes, this is time, it's not speed. So let's be careful, guys, there. This is seconds, yes, time, seconds, right? We don't need distance. That's it. Very good, guys. Excellent. 5 seconds. It's all what it takes, right? They're not asking you for what's the distance, just for the time in this case. Great. Now, let me talk about this guy. I think it's this one. Yeah, we did one of these. I think you can follow the example that I worked out in the notes for this, but this one I think doesn't have example number 7 and 8. Yeah, this one is the same as this, similar, but the 8 I think it doesn't have. So let me go over this. I want you to have this well understood. It says a rock is thrown vertically upward from the surface of an airless planet. It reaches a height of s equal 120 t minus 60 square meters in t seconds. How high does the rock go? How long does it take the rock to reach its highest point? Okay. Okay. So the ball is thrown up, right? It reaches certain height and comes back, right, on this planet. Okay, and then good news, we have the function that gives you the position at any given time, right? They are asking you how high does the rock go, right? And also how long it takes for the rock to reach this high point, right? How high, this height, right? Now, one thing is true, ball will reach its highest point when look, notice the velocity is 0, right? Velocity 0, because it's going up here, velocity 0, and then comes back, right? When velocity equals 0. So all we gotta do is get our velocity from our position function, right? Via taking the derivative, right? And then set that equal to 0. That will tell us, right? What is the time that corresponds to this highest point? Let's say this is our XY coordinate system. Here, XY coordinate system. And then we are trying to find out, right? What is the time here for this to happen, right? This is the position function. Let's find the velocity by taking the derivative of the position function, right? Derivative of this position function will be 120t. The derivative of that is just 120 minus here, derivative of this part, 2 coming down, multiplying 6, 12. T stays raised to 1 less is 1, right? This is the velocity function. Right, now set v equal to 0 and solve for t. That's gonna give us the time, right? So we're gonna set this guy equal to 0, solve for t, and that should give us the time. Dividing both sides of this equation by -12, we are gonna get that this will happen at t equals, look, negative, positive 12 into 120, 10, right, 10. After 10 seconds, the ball will reach its maximum height, right? It will be here, just 10 seconds. Okay, that's one of the answers, but they also want that actual maximum height, right? H max, the maximum height. So the maximum height will be then the height associated to this time, right? So maximum height will be equal to the function, which is this, evaluated at 10, right? Time 10. So -6 times 10 squared. Let's compute it in our calculator. Okay, so that's going to be 120 times 10 minus 6 multiplied by 10 squared. 600, right? 600. So that is 600. And remember, we are measuring this in, I think, meters, right? 600 meters. That should be the maximum height. So time 10 seconds, maximum height 600 meters, right? You follow, guys? 600 meters here. So it should be this, right? Very good, very good.